Guys, right now we'll be starting with the second property, which we are going to study the trends of. Now, you know what is the meaning of trends. We have already done the trends in the case of atomic size. What we had basically done is that we had seen as we go from left to right in the periodic table, what happens to atomic size. We had seen that it decreases, and we had also seen that as we go from up to down in the periodic table, what happens to atomic size, that is, it increases. Now we had discussed about all possible factors which affected atomic size, and we had calculated the atomic size as we went from up to down in the periodic table and as well as from left to right in the periodic table with regards to atomic size, considering all the factors affecting it. In a similar way, my dear friends, right now we will be talking about ionic size. You already know what is the meaning of an ion, right? An ion is nothing but a positively charged or negatively charged atom or group of atoms. So, firstly, the one thing which you need to know before we even start up is that the trend of ionic size will be very similar to the trend of which is observed in the case of atomic size, and hence we are not going to plot separate graphs for it. So in the case of ionic size, you guys need to understand that as we go from left to right in the periodic table, the ionic size generally decreases, and as we go from up to down in the periodic table, ionic size generally increases, which the trend which is very similar to that of atomic size. However, the exact details will be a bit different. In some cases, means it will not increase or decrease with the same level or exactly with the same pattern as observed in the case of atomic size. However, I have just given you the general trend. Now, before we start, let us first see what is the meaning of an ion. We already know what is the meaning of an ion, right? An ion basically means, if in case we just quickly give few examples for it, we already know that in the case of ion, we can have like sodium atom. It has an electronic configuration, say for example 281, and it forms sodium ion by giving away one electron, right? In a similar way, we can also have fluorine ion which is formed. Fluorine whose atomic number is equal to 9, hence its electronic configuration will be 2,7. Now in this case, fluorine will in the opposite situation that of sodium, fluorine will accept an electron, right? In the case of fluorine, it will be accepting one electron and it will be forming fluoride ion, that is F-1 or F1-, whichever way. So basically, in short, fluorine here forms a negative charged ion, because this fluorine here, it is nothing but a charged atom, an atom which has a charge on it. This is also a charged atom, that is sodium atom which has a charge on it becomes sodium ion. This is fluoride ion. Now, right now, we will not be considering the size of these atoms. Here, we will be considering the size of these ions. And this part becomes quite interesting. Because imagine that in the case of sodium, when it had 3 shells, because it earlier had 3 shells, and now after giving away its 1 electron, now it will be having 2 shells, and due to which the atomic size, the ionic size in this case, will be much less than the atomic size in the case of sodium. In the case of sodium, hence, we will be observing that the atomic size which is observed in the case of sodium will be atomic size in the case of sodium will be 186 degree Armstrong, and in the case of the ionic size of sodium, it will be around 95 Armstrong. So now with this you can understand that the ionic size in the case of sodium, it is much lesser as compared to, this is ionic size. Let's write it down so that there is no confusion. This is ionic size, this is atomic size. As you can see, my dear friends, here the ionic size is much lesser as compared to the atomic size, because of the simple reason that we basically have one less shell. And as I told you, the main reason for the size of an atom or an ion is because of the number of shells. Now, before we move ahead, let us first see how do we calculate ionic size. Because we had seen how to calculate atomic size, we had done a separate video for it, right? We had considered we had considered covalent radius and different types of radius. Now, here we will be considering the ionic radius, because here we are trying to calculate the size of an ion. Now, to calculate ionic radius, obviously we need to go into a compound wherein ions are already present, right? Let us go into that. So if in case we have a compound wherein we have positively charged and negatively charged ions which are already present, let us consider that. So here we will be having Na plus ion and we will be having Cl minus ion. So these are the two types of ions which we have in the case of sodium chloride crystal. So what we do is that we look at both these ions and we calculate their sizes. So if in case we have sodium ion, if in the case of sodium chloride, this is the radius which is occupied by sodium ion, and say for example this is the radius which is occupied by chloride ion. In that case, what we do is that we simply calculate the distance as we normally do between the nucleus of the two ions. So if here is the nucleus of sodium ion and here is the nucleus of chloride ion, we simply calculate the distance between them, and that distance between them we divide it by 2, and therefore it becomes the ionic size. So this is how we calculate the ionic size. Now there is one thing which you guys need to understand, is that in the case of ions, the ionic size of negatively charged ions which are called as anions, right? In the case of anions, the size is much larger as compared to in the case of cations. The size of cations is much lesser as compared to the size of anions. Now the reasons we are going to study systematically. I could have given you the reason here itself, but we are going to study systematically exactly in the way that we have studied the factors which were affecting the atomic size. And we had considered each and every factor affecting atomic size, and after that we had given even weightage to the different factors of determining atomic size on the basis of their importance, on the basis of their final effect on the atomic size. And on the basis of, after doing plus minus, we had calculated that the net, there will be an increase, or net there will be a decrease in atomic size. So in a similar way, my dear friends, we also have to do it very systematically here, because it is possible that all the factors which might affect ionic size might not increase or decrease together. There might be a situation wherein few of the factors go in one direction and few of the factors might go in other direction. When I say direction, I basically mean that few factors will increase the ionic size, and according to few factors the ionic size should decrease. So we'll have to calculate finally on the basis of how many factors are going against means because of how many factors ionic size will increase and because of how many factors ionic size will decrease, and we are going to calculate the addition. We are going to do the addition subtraction of these factors in terms of their importance, and then we'll do the net calculation, and with that we'll look at the net effect on the ionic size, and on the basis of that we can understand whether the ionic size increases or the ionic size decreases. Now here let us look at the factors which affect ionic size. Now here we are not going to look at factors like screening effect, because if in case, say for example, we are looking at molecules or ions like say sodium ion and fluoride ion, let's say for example, in that case we know that in the case of fluoride ion, even it will have an electronic configuration of 2,8, and even sodium will have an electronic configuration of 2,8, right? I hope so you understand. If in case you don't, let us see. Let us complete this part then in the case of fluoride, because in the case of fluorine we had seen, in the case of sodium we had looked at the atomic as well as ionic size, right? Let us complete what happens in the case of fluorine. In the case of fluorine, what happens to the ionic size as well as atomic size, and then we will move ahead. In the case of fluoride ion, the electronic configuration obviously becomes 2,8, right? Because after having an electronic configuration of 2,7 in atomic form, it will accept one electron, and after accepting one electron, it will form 2,8. After it does so, we now know that the sizes of the atoms and ions in the case of fluorine can also be compared as follows. In the case of fluorine, if in case we consider the atomic size, it will be 72. Let's write down the atomic size in the case of fluorine will be 72. Let us consider degree Armstrong or Armstrong degree. In the case of fluorine, if in case we consider the ionic size, it will be 136 degree Armstrong. So as you can see, my dear friends, here the ionic size in the case of fluorine, fluoride ion, here will be much larger in this case as compared to the atomic size, because of the simple fact because of the increase in the number of electrons and hence the increase in the repulsion of electrons. My dear friends, we are going to do this part totally in detail. However, at this point itself, I need to remind you what happened in the case of noble gases when we had studied the atomic size in our last video. We had seen that in the case of atomic size, when we calculate the atomic sizes, then we have seen very, very clearly that when we move from the halogens to the noble gases, then because of the increase in the number of electrons to the maximum possible, the inter-electron repulsion, it increases to a very large extent, and hence instead of the atomic size decreasing, the atomic size increases to a very big extent from fluorine to, say for example, neon, or from chlorine to, say for example, argon. So that is the factor, that is the main factor which has driven the ionic size in the case of fluorine F minus to be much larger than in the case of the atomic size, because when after accepting one electron, the fluoride ion, its ionic size, it increases because of the repulsion between electrons. The electrons, because there is a huge repulsion between electrons, the electrons want to move away from each other as much as possible for increase in stability. As you guys know, all these systems naturally they want to go from an unstable state to a stable state. So therefore, to become more stable, in that effort, the electrons, they repel each other to such an extent that the ionic size increases to as much greater as possible. Hence, in this explains that the ionic size in the case of fluorine is much greater as the atomic size. Now, once we have just dipped our fingers into the concept of ionic size, let us now do it in more detail, in comprehensive detail, starting with the factors which are affecting the ionic size. The factors which are affecting ionic size can be given as follows. Let us write down the first factor, and obviously the most important factor. The first factor and the most important factor will be the number of shells which are involved, right? Which was a factor which was very similar to in the case of atomic size. Even that had the greatest weightage in terms of the atomic size. The second factor which we can consider will be the nuclear charge. See, when we talk about nuclear charge, we are actually basically talking about the effective nuclear charge. What is the difference among them? Let us see. Now, effective nuclear charge basically means that the amount of nuclear charge per electron, which is effective nuclear charge, which basically means that if the nuclear charge is distributed in terms of more number of electrons, in that case, we say that the effective nuclear charge has decreased, and hence the decrease in atomic size, which should have been there, will not be as much as it is expected. So I hope so, my dear friend, that you understand. See, if in case we have more number of electrons for the same number of protons, if we have more number of electrons as observed in the case of fluorine, right? Let us take a practical example in front of our eyes. In the case of fluoride ion, we have the same number of shells. Even here we had 2 shells, and even here we have 2 shells, right? So therefore the number of shell is the same. So therefore the first factor has no effect or no role to play in this specific case. However, you might surely observe that here 1 electron has increased in the case of fluoride ion. Because of the increase in the number of electrons, what happens is that there is a repulsion between the electrons, due to which the ionic size, it is more than atomic size, that we have already discussed. Now here is another factor which I am bringing into play here. The other factor which I am bringing into play here is the effective nuclear charge. In the case of fluorine, we know that because the atomic number of fluorine is equal to 9, we will be having, in the case of fluorine, exactly 9 number of protons. And we know that protons determine the total amount of positive charge which is present inside the nucleus, right? And because the earlier there were 9 electrons which had force of attraction with the nucleus which contained 9 protons. However, after it accepted 1 electron, it now has 10 electrons which now has a force of attraction with the same number of protons, which is 9 protons. As you can see, the effective nuclear charge here has decreased because the same amount of nuclear charge is now spread with more number of electrons, and hence we can say that the effective nuclear charge in the case of fluorine, it has decreased. So even in the case of fluorine, the first factor will not play any role. However, the second factor, which is effective nuclear charge, will play a role. So whenever we talk about nuclear charge, we talk in terms of an effective nuclear charge. So I hope so, my dear friends, that you have understood now what is the meaning of effective nuclear charge, and you will be able to answer questions, objective type questions or like short questions, if in case you have been asked about what is the meaning of effective nuclear charge. Once we have written down this factor, we also need to write down the next factor, which is the inter-electronic repulsion. Right? We also know that in the case of fluorine, as we have already discussed, there is inter-electronic repulsion which is observed. Also, to some extent, there will be a screening effect which might be observed in some cases. So let's write it down. Now, my dear friends, screening effect will be more applicable, or it will be more observed when we are talking about going from up to down in a periodic table. So obviously, as I had explained to you in very much detail in the last video, whenever we go from up to down in the periodic table, we have a situation wherein we will be having a gradual increase in the atomic size, and in this case, a gradual increase in the ionic size. So let us now study what happens now as we go from left to right in the periodic table with respect to the ionic size. Let us now see what happens as we go from in the case of the negatively charged ions. Now we know that if in case we consider the isoelectronic species, what is the meaning of isoelectronic species? Now, isoelectronic species will be a species like in the case of sodium Na plus ion and fluoride ion. In the isoelectronic species, let us write down the meaning, the term isoelectronic species, right? Isoelectronic species. In the isoelectronic species, example will be sodium and fluorine, because as you can see that after the ion formation, the total number of electrons here is the same. So hence, if in case we have an isoelectronic species, the greater the amount of the positive charge which is present in the specific positively charged ion, which is the cation, there will be a further decrease in the ionic radius because of the increase in the positive charge, that is because of the increase in the effective nuclear charge. Let us discuss this in detail. Right now we will restrict ourselves to what happens when we have the positively charged ions having the same number of shells. Now after we consider them, we will be considering the negatively charged ions having the same number of shells. And finally, we will be going into a situation where we have positively charged ions as well as negatively charged ions having the same number of shells, which are isoelectronic species, as we have already explained in the case of fluorine and sodium. This will get quite interesting. Let us first see what happens in the case of Na plus ions, that is in the case of cations. Starting with in the case of Na plus ions. We know that in the case of Na plus ions, after ion formation, we will be having an electronic configuration of 2,8, right? In the case of magnesium, we know that after giving away 2 electrons, magnesium electronic configuration is 282, right? Because its atomic number is equal to 12, and hence after giving away 2 electrons, it will get a charge of 2 plus on itself, right? and after getting a charge of 2 plus on itself, it will have an ionic electronic configuration of again exactly the same as in the case of sodium ion. So friends, in the case of magnesium ion, as we can see, the amount of the positive charge here is plus 2, and hence in this case we can see that the electronic configuration in the case of magnesium ion is the same as electronic configuration in the case of sodium ion, and hence we can say that these are isoelectronic species. So isoelectronic species means two species which might have different charge on itself in terms of ions. However, they will have the same number of electrons which are present. Again, we can quickly go to aluminium. In the case of aluminium, we know that aluminium has a charge of plus 3 on it. Why? Because aluminium has an electronic configuration of 2, 8, 3. Because if in case it gives out 3 electrons, then it will have a total number of electrons of 2, 8 in itself. So therefore, we will be having 2, 8 number of electrons in the case of aluminum ion as well. As of now, let us restrict ourselves to in the case of aluminum. What happens as we go from sodium ion to aluminum ion? Let us look. In the case of sodium ion, if in case we look at the amount of the positively charged protons which are present inside the nucleus, obviously it will be equal to the atomic number, right? Now everybody knows that the atomic number in the case of sodium is equal to 11. So let's write down. In the case of sodium, we have total 11 number of protons which are present inside the nucleus, as I have written it down. Again, in the case of magnesium, we have total 12 number of protons which are present inside the nucleus. In the case of aluminum, we have total 13 number of protons which are present inside the nucleus. As you can see, the number of electrons is the same. We are not arguing about that. Here, the number of electrons is the same. But as you can see, the nuclear charge, it has decreased. In the case of magnesium, the number of electrons is the same, but the nuclear charge is more. In the case of aluminum, the number of electrons is the same, however, the nuclear charge is more. Hence, we can say because the nuclear charge is more per electron, because the number of electrons is the same, right? So, we can say that the effective nuclear charge, that is a total amount of nuclear charge per electron, the effective nuclear charge here, it increases as we go from sodium to aluminum. Hence, when we are talking about this particular fact, we can see that the effective nuclear charge, it is increasing as we go from left to right in the periodic table. Let us now look at the other factors in this specific case. The other factors here will be, firstly, the number of shells. The number of shells in all of them will be the same, right? Because they have 2, 8, that is all of them have 2 shells, right? So therefore, the number of shells in all these situations will be the same. Hence, the number of shells here will be equal to 2. So hence, this is a wash. Wash means basically all of them have the same thing, right? So therefore, that this particular factor is neutral. So there is no different distinguishing factor here. This is not a distinguishing factor between all the 3 of them. So that's what we call as wash in English. So the next thing will be interelectronic repulsion. In this case, the interelectronic repulsion will be the same, right? Because the number of electrons in all of them will be the same because they are isoelectronic species. So hence, in this case, we can consider this factor also to be a wash because the number of electrons are the same. Hence, the amount of repulsion between electrons will also be the same. Let us now look at screening effect. My dear friends, here there is no question of screening effect being more or less because again the number of electrons is exactly the same. And hence we can say that the effect of screening effect will also be a wash. So here the only factor which is affecting the ionic size will be the effective nuclear charge. And as we can see, because of the effective nuclear charge which is increasing from sodium to aluminum, we can say that as we go from left to right here in the same shell, as we go from left to right, the ionic size here, it will decrease. The ionic size will decrease because of the effective nuclear charge being more, the outer electrons, that is the second shell electrons, will be pulled towards the nucleus, which are with a much larger force. Let's write it down so that we understand it better. In the case as we go from sodium to aluminum, what happens here is that the effective nuclear charge, it increases, right? And because the effective nuclear charge, it increases, the electrostatic force of attraction between the outer electrons, that is these 8 electrons, and the nucleus, it increases, right? Because it increases, electrostatic force of attraction increases between the outer electrons and the positively charged nucleus. Hence, the outer electrons will be pulled that much towards the nucleus. The more the force of attraction, the outer electrons will be pulled that much towards the nucleus, right? So therefore, the atomic, in this specific case, the ionic size, it decreases because of the pulling of outer electrons towards the nucleus. So this is the conclusion that we have reached. What will happen as we go from sodium ion to aluminum ion. Now, it is time to now consider what will happen if in case we talk about the negatively charged ions. Let us talk now about the negatively charged ions. So if in case we talk about the negatively charged ions, we need to write down the negatively charged ions before sodium. So if in case we do that, or we can also consider the negatively charged ions after aluminum, which are nothing but like phosphorus ion, which is P minus 3, or sulfur ion, which is S minus 2, or chloride ion, which is Cl minus. On the other hand, here we can write down about the negatively charged ions before sodium. In that case, obviously, we will be talking about nitrogen, oxygen, and fluorine. The point is that the net effect which will be shown here, that is the conclusion that we will be reaching here, will be exactly the same conclusion that we will be reaching here also, if in case we consider chlorine instead of fluorine. So it like depends totally, whichever example you can consider. You want to consider this example, you can consider this example, or you can consider the example of chlorine as well. As of now, let us continue with this here, and let us consider the example of fluorine. You could have easily taken that example, so that's not a problem. You will reach the same conclusion. So here, if in case we consider the example of fluorine, we know that after fluorine there is a noble gas neon, right? So right now we are not considering neon into the picture. So if in case we consider fluorine here, before fluorine, we know that we have oxide ion which is present. Oxide ion basically means O2 minus ion, wherein we have oxygen atom which is accepting 2 electrons from outside, wherein we know that the atomic number of oxygen is equal to 8, its electronic configuration is 2,6, wherein it will be accepting 2 electrons from outside, and after it accepts 2 electrons from outside, it will become an oxide ion. And in the case of oxide ion, we will be having more number of electrons, that is, we will be having again the number of electrons increased by 2. Here in the case of fluoride ion, after it accepts the electron, the number of electrons increases by 1. So hence, let us now talk about the ion which will be before it. That will be in the case of nitride ion. That is in the case of nitrogen ion. In the case of nitrogen ion, we will be having a situation wherein we will be having 3 minus charge on nitrogen ion. So in the case of all these 3 cases, let us look at their electronic configurations after the ion has been formed. We are not concerned with the electronic configuration in atomic form. We are now concerned with the electronic configuration after the ion has been formed. Let us look at it. We now know very clearly that in the case of all the 3 of them, it will have the same electronic configuration, that is the exact same which has been written here in the case of the positively charged ions. In the case of fluorine, after it accepts 1 electron, 2,7. After it accepts 1 electron, it forms 2,8, right? So we can write it down. It forms 2,8. In the case of oxide ion, we know that it will form an electronic configuration again of 2,8. In the case of nitride ion, we also know now after nitrogen atomic number 7, 2,5 electronic configuration accepts 3 electrons, forms 2,8. So therefore, even in the case of nitrogen ion, we will have an electronic configuration of 2,8. As you can see, the electronic configuration for all of them is the same. Hence, the electronic configuration part will be the number of electrons, the factors related to number of electrons will be a wash here also. Now let us look at the number of protons which will be applicable here. So the number of protons which will be applicable here will be in the case of nitrogen, because its atomic number is equal to 7, hence its number of proton also will be equal to 7, right? So let's write it down. So here the number of protons is equal to 7 proton. In the case of oxygen, the number of proton obviously will be equal to 8 proton because its atomic number is equal to 8. Fluorine atomic number 9, therefore 9 protons. Now let us look at the different factors which are affecting the ionic size. If in case we move from nitrogen ion to fluoride ion, that is, as we move from left to right in the periodic table. Let us now also calculate the net effect which is observed here. Now here, as we can see, the effective nuclear charge, if in case we consider all the three of them, let us now consider these different points. So here the number of shells is the same, so this factor is a wash. Hence, let us now talk about the inter-electronic repulsion. Inter-electronic repulsion will be the same for all of them because the electronic configuration is the same. So this factor is also a wash. Next, let us talk about the screening effect. Screening effect will also be a wash because here the amount of electrons is exactly the same. The same electronic configuration is present in the case of ions. However, therefore, the only factor which will now play a role will be the effective nuclear charge. Hence, in this case, if in case we consider the effective nuclear charge, that is the number of protons divided by the total number of electrons, we can see that in the case of fluoride ion, the effective nuclear charge will be much more than in the case of nitride ion. However, there is, if in the case of fluorine, hence we will be having more amount of effective nuclear charge. Let us see what happens as we go from left to right. Let's write it down in a similar way as we had written in the case of the positively charged ions. Therefore, as we go from left to right in the periodic table, that is, as we go from nitride ion, nitrogen ion to in the case of fluoride ion, we can see that the effective nuclear charge, it has increased as we go from nitrogen to fluoride ion. So therefore, as the effective nuclear charge increases, as we have already seen, the electrostatic force of attraction, it will also increase. As the electrostatic force of attraction increases, therefore the ionic size decreases. So the same thing happens in the case of the negatively charged ions as well. That is, as we go from left to right, the ionic size, it decreases from nitride ion to fluoride ion because the total number of electrons is the same. Therefore, the only differentiating factor is the nuclear charge. Hence, the effective nuclear charge, as it is increasing, hence the electrostatic force of attraction increases and hence the ionic size decreases. Once we understand that, we now need to go to the last part wherein we are comparing the positively charged ions and the negatively charged ions, which we have, my dear friend, already compared, right? If in case we consider the size in the case of fluoride ion as well as in the case of sodium ion. So right now, when we are comparing the positively and negatively charged ions like sodium and fluorine, let us see what happens. It is extremely interesting. Now, if in case we look at the atomic size, when we are talking about the fluorine atom and sodium atom, as we had seen in the last videos, we know when we had compared the atomic size, we know that as we move from fluorine atom to sodium atom, because there is an increase directly of one particular shell, hence because the increase in the number of shells is the number one and the most important factor which affects atomic size. Hence, as we move from fluorine to sodium, the number of shells increase from 2 to 3, right? Because in the case of fluorine, in the case of fluorine atom, the electronic configuration was 2,7, hence the number of shell being 2. In the case of sodium atom, the electronic configuration being 281, hence the number of shells being 3. Because the number of shell increases by 1, hence if in case you consider the atomic size of sodium, it was much greater than the atomic size of fluorine. Let us look at the numbers that we have got. This was the atomic size of sodium and this was the atomic size of fluorine. As you can see, there is a huge increase in the atomic size from fluorine to sodium. There was a huge increase in the atomic size because of an increase directly in the number of shells. However, in the case of ionic size, the situation will be a bit different. How it will be a bit different? Let us look. When we are talking about ionic size, the number of shells is the same. The inter-electronic repulsion will be the same because of the same electronic configuration. Screening effect will have no part to play. Hence, the only factor which will have a part to play will be the effective nuclear charge. As we know, my dear friends, in the case of sodium, the effective nuclear charge is more. Hence, the electrostatic force of attraction between the electrons and the nucleus, it will be more. Hence, because the electrostatic force of attraction is more, therefore the nucleus will be attracting the electrons, outer electrons, valence electrons closer to itself, hence there will be a decrease in the ionic size. Hence the sodium's ionic size will be lesser than in the case of fluorine. Let us look if in case what I have taught you actually matches the numbers that we get. In the case of ionic size, as you go from fluorine to sodium, as you can see, the ionic size, it decreases because of the exact factor which I have told you, because of the increase in the effective nuclear charge. Effective nuclear charge means number of protons divided by number of electrons. So here it is 11 upon 10. In the case of fluorine, it was 9 upon 10. So here, because 11 upon 10 is greater than 9 upon 10, here the effective nuclear charge will be more, electrostatic force of attraction will be more. Here the ionic size will be lesser in the case of sodium, because the positively charged nucleus will attract the negatively charged electrons toward itself, leading to a decrease in ionic size in the case of sodium as compared to in the case of fluoride ion. Hence, as you can see, the interesting point that I was trying to drive home was that, look at the interesting point. As we go from fluorine to sodium atom, the atomic size, it increases to a very large extent. However, if in case we look at the ionic size between from fluorine to sodium, it should also have increased as in the case of atomic size, right? However, it is not increasing, it is decreasing. So here, as you can see, there is a decrease in the ionic size because of the only effect which is applicable here in the case of calculation of ionic size, that will be the effective nuclear charge. So I hope so, my dear friends, that you have understood how the ionic size, it affects the particular group as well as periods when we are concerned about the effective nuclear charge, which is the only factor which is applicable. If in case you require, we can also talk about the ionic sizes of the ions which are present in the same period as in the case of sodium, magnesium and aluminum. However, in their case, the ionic size will be much larger because of the increase in the number of shells. So the number of shell then becomes a very important factor. Let us quickly understand that, so that there is you don't make a mistake in that. In the case of, let us now consider silicon to be a wash, because in the case of silicon, we know that it can, accept electron, it can take electrons, so it can have a charge of +4, -4. So let us not consider silicon because it is a borderline case. Let us now consider very clear-cut cases, starting from in the case of phosphorus, which can directly be compared with the case of nitrogen. So therefore, when we are talking about phosphorus, it will have a -3 charge, that is phosphide ion. In the case of the next atom, which is sulfur, it will have -2 charge. In the case of chlorine, it will be -1 charge. My dear friends, I will be going a bit fast here because you already know the entire exercise, right? So next, we are going to write down the electronic configuration. In the case of phosphorus, it has original electronic configuration as 2, 8, 5. After accepting 3 electrons, it will now have an electronic configuration of 2, 8, 8. In the case of sulfur, it will be also 2, 8, 8 because its electronic configuration is 2, 8, 6, atomic number 16, accepting 2 electrons, forming 2, 8, 8. In the case of chloride ion, again, as you guys already know, 17 atomic number, 2, 8, 7 electronic configuration, accepting 1 electron, it will form 2, 8, 8. Hence, in the case of chloride ion, also electronic configuration is the same. The same electronic configuration in all of them. Hence, because the same electronic configuration is there, hence, when we compare them, the comparison will be same as compared to this. But right now, what we are trying to do is we are not trying to compare all the 3 of them, because we know the conclusion beforehand, right? This match is fixed. We know that as we go from left to right, blah, 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 because all these factors, the ionic size will finally decrease. We are not talking about that, because here the trend between the 3 of them will be exactly the same trend in between all the 3 of these, in between them. But right now, we are not talking in terms of the 3 of them. Right now, we are trying to talk in terms of the ionic size of these 3 positively charged ions as well as the 3 negatively charged ions. We are trying to talk about the difference between them, between these 3 and these 3. What will happen? We have already seen the difference between these. We have already seen what happens as you go from here to here. We have already seen that the ionic size, it decreases. We have just shown you in terms of numbers right now. It will be interesting, my dear friends, to cover this part also, because if in case I don't cover this part, the comparison between this and this, there will be a void which will be left in your knowledge. So let us quickly do it once we know what are the factors affecting rate, right? In this specific case, let us renew the understanding of the factors which will be affecting this. As we see in the case of from aluminum to phosphorus, when we are going from aluminum ion to phosphide ion, as we can see, the number of shell has increased, right? So here the number of shell, as we go from aluminum to phosphorus, the number of shell has increased. What has happened to the effective nuclear charge? In the case of aluminum, we had an effective nuclear charge of, let's write it down below it itself, that will be better, right? In the case of aluminum, the effective nuclear charge was 13 upon 10. In the case of phosphorus, if in case we look at the effective nuclear charge, we know that in the case of phosphorus, the amount of positively charged protons is equal to 15 proton, 16 proton, 17 proton. So therefore, here the amount of protons is equal to 15. However, here the number of electrons here, as you can see, is equal to 18. So if in case we want to calculate the effective nuclear charge, we have here the value of 1.3, which was very simple to calculate, right? But if in this specific case, the value will be lesser than 1, it will be lesser than 1, right? Here it is greater than 1. As you can see here, the effective nuclear charge is less in the case of phosphorus as compared to in the case of aluminum. In the case of as we go from phosphorus to chloride ion, we know that the effective nuclear charge, it will keep on increasing as we go from here to here. The effective, as we had seen here, the effective nuclear charge will keep on increasing. But that is not the point. The point is that as we go from aluminum to aluminum ion to phosphide ion, as we can see, the effective nuclear charge, it decreases. So therefore, here there is a decrease in the effective nuclear charge. When we are talking about inter-electronic repulsion, in both these cases, the inter-electronic repulsion will be very much comparable. However, because in the case of phosphide ion, because of the increase in one shell, there will be, because the more number of electrons they are present, the inter-electronic repulsion will be slightly more. So hence I am just showing a small arrow because there will be just slightly more number of electrons because of the presence of total number of electrons more, that is 18 electrons as compared to here 10 electrons. When we are talking about screening effect, here there will be more amount of screening effect. So here the amount of screening effect will increase. Once we know the effect of all these factors, now then finally let us conclude in this last part that as we move from these positively charged ions to the negatively charged ions in the same shell, let us see what will be the net effect. The answer is actually very obvious for those people who have listened to me very properly up till now, because we know it that as once the number of shells, which is the most important factor, it is towards one side, the entire game is over, because that is the most important factor which affects around 70 to 80% of the entire decision making process. So as you move from sodium to as we move from the positively charged ions to the negatively charged ions in the same shell, which in atomic form which were in the same shell, obviously here the number of shell has increased, right? To be exact, we know that as the number of shell increases, therefore the ionic size here will be much greater than the ionic size in the case of the positively charged ions. Hence, the ionic size, as we go from left to right, let us draw the conclusion. The conclusion is that the ionic size here, it increases as we go from this part to this part. I hope so, my dear friends, that you have understood the importance of the number of shells in the calculation of the ionic size. So this, and also when we have written the heading of ionic radius, and however there should not be any confusion, because initially when we have talked about atomic size, I had made it very clear to you guys that when we are talking about the ionic size itself means radius. So when we are talking about ionic size, we are talking about ionic radius. So this was everything, my dear friends, in detail about how we calculate ionic size, as well as how we look at the trends of ionic size when we go from positive to negatively charged ions, as well as from the negatively charged ions to positively charged ions in different shells, as well as the difference in the same shell, as well as as well as what happens in the case of isoelectronic species. So if in case you have a slight understanding problem in any of these, please rewind the video and just rewatch the video so that you can understand it perfectly. Friends, here I have got a question for you which is related to the atomic and ionic size, which you need to solve it by your own. So the question here is as follows. Here we have been given 2 atoms and 2 ions, and we need to arrange all of them in terms of their increasing atomic size. That is starting from the least atomic means least size to the largest size. You need to arrange all these atoms as well as ions, all the 4 of them, in a particular order. I want you guys to pause this video and to try to solve it by your own. And on the other side of this video, I'll be solving this question for you. So best of luck for it. So guys, let us now try to solve this question. So here, first of all, let us compare the species which are similar to each other, and then we'll be comparing finally the species which are dissimilar to each other. First of all, as we can already see, here we have 2 similar type of species which are ions, positively charged ions. Both of them are isoelectronic species. You already know what is the meaning of isoelectronic species. It will be those species which have basically the same number of electrons. And once we compare both of these, then we'll be comparing the neutral atoms like magnesium and aluminum. Let us do so. Let us compare all of these, like the pairs of the pairs in isolation to each other. First, let us see what happens in the case of magnesium and aluminum. If in case we arrange aluminum and then magnesium, we know that as we move from left to right in the periodic table, the atomic size decreases, right? And because the atomic size decreases as we move from left to right, aluminum is in the periodic table. Aluminum comes on the right hand side of magnesium, and hence the atomic size of aluminum will be lesser as compared to in the case of magnesium. And hence because the atomic size of aluminum will be lesser as compared to in the case of aluminum, we can arrange aluminum here on the left hand side of magnesium, right? So once we understand that, we need to now understand the relationship between magnesium ion and aluminum ion. So let's write them down as well. So if in case we write down say aluminum ion, first I'm writing it down just randomly, aluminum ion, and then I'm writing down magnesium ion. So let us now compare both of them. My dear friends, we have already completed this part when I was giving you the explanation, right? So here in this specific case, we know that the electronic configuration of aluminum and magnesium, both of them will be the same, that is 2,8 and 2,8. Because magnesium, after means giving away 2 electrons, it will form 2,8. Aluminum, after giving away 3 electrons, it will form 2,8. However, the differentiating factor will be the number of protons which is present in the nucleus. That is the nuclear charge, which is also called as the effective nuclear charge. Here in this case, the nuclear charge is equal to 13, and in this case, the nuclear charge is equal to 12, which are basically their respective atomic numbers. So therefore, here in the case of aluminum, 13 electrons will be pulling this 8 electrons toward itself, and here only 12 protons will be pulling 8 electrons closer to itself. So here the force of attraction will be much stronger in the case of aluminum, due to which the outer electrons will be attracted much stronger to the nucleus, hence the atomic size will decrease to a much larger extent. Hence here the atomic size will be less as compared to in the case of magnesium ion. So if in case we need to arrange them, the arranging order will be like this, wherein the atomic size of magnesium ion will be greater than the magnesium ion will have greater size as compared to the aluminum ion. Once we understand that, we need to finally join all the 4 of them in terms of size. So here is one place where you guys need to understand the relationship between aluminum ion and magnesium atom. The one thing that we need to understand is that here in the case of aluminum, the number of shells is equal to 2, right? However, if in case we look at magnesium atom, the number of shells is equal to 3, because we have total 282 electronic configuration. Atomic number of magnesium is equal to 12, as we have already seen. So here we will be having total number of electrons as equal to 12, and here we have the total number of electrons in the case of magnesium as equal to 10. Hence the electron here will be having 2 shells, here we will be having 3 shells. As we have seen, the number of shells is the number one, the most important prioritized reason of the increase in atomic size. Atomic or ionic size, whichever situation it is. So here in the case of magnesium, because there are 3 shells, its size will be much greater as compared to in the case of magnesium ions, or as well as in the case of aluminum ions. In both the cases we have only 2 shells which are involved. So once we understand this, we can write down the entire order as follows. That is, we can write it down as aluminum ion, which has the least size of and before aluminum will be obviously be having a magnesium ion. It is just before it, and then we know that the atomic sizes will be much greater as compared to ionic sizes. Hence we can write it down this also in the same order, wherein we know that aluminum was having a lesser atomic size as compared to in the case of magnesium. So this is how we write down the order which has been asked in terms of increasing atomic size. So therefore, if in case we show the increase in atomic size, in the case of aluminum the atomic size will be least, in the case of magnesium the atomic size will be more, in the case of aluminum the atomic size will be still more, in the case of magnesium the atomic size will be still more. So this is how we show. This is the atomic size of aluminum, this will be that of magnesium ion, this will be that of aluminum atom, and this will be again in the case of magnesium atom. So this is how the atomic sizes will be related between all these 4 different species. So if in case you have got the answer correct, congratulations.